The first three patterns in a sequence of patterns of tiles are shown in the diagram below. In part A, we're asked to draw the next pattern of tiles onto the diagram above. To draw the next pattern, we must identify the structure that's generating these shapes. In pattern 1, we have 3 squares across the top and 2 squares down each side. In pattern 2, we have 4 squares across the top and 3 squares down each side. In pattern 3, we have 5 squares across the top and 4 squares down each side. The pattern here is that the number of squares across the top and the number of squares down the side both increase by 1 each time. Continuing this, pattern 4 will have 6 squares across the top and 5 squares down each side. Part B says the following. Based on the pattern shown, complete the table below. The first row is filled in for us, and it says that pattern number 1 contains 5 tiles. To fill in the blanks in the table, we must determine the number of tiles in the second, third, fourth, and fifth pattern. Well, we already have patterns 2, 3, and 4 drawn, so we can simply count up the number of tiles in each of these patterns. When it comes to pattern number 5, we don't have the pattern drawn out. One option would be to draw out the pattern and count up the number of tiles, but this would be quite a bit of effort. A more clever approach would be to look at the sequence of the number of tiles and see if we can spot a pattern. Our numbers are 5, 8, 11, and 14. The pattern here is that each number is 3 bigger than the previous one. So the next value would be 14 plus 3, which is 17. Looking back at our diagrams, the plus 3 pattern makes a lot of sense. Essentially, each time we're adding 1 new square across the top row and 1 new square in each of the 2 vertical legs. Assuming the pattern continues, the number of tiles in the nth pattern of the sequence is given by the formula Tn is equal to Pn plus Q, where P and Q are elements of the natural numbers. Find the value of P and the value of Q. In part B, we filled out a table which contains the number of tiles for the first few patterns. And we saw that there was a pattern in this sequence. To get from each number to the next, we added 3. This is referred to as an arithmetic sequence. The following result from page 22 of the formula book will be quite helpful. Tn the nth term of an arithmetic sequence with first term a and common difference d is given by t of n is equal to a plus n minus 1 times d. To apply this result, we'll need to identify the first term a and the common difference d. In our sequence, the first term is a 5. The common difference refers to the number which is added to get from one term to the next. Here, our common difference is 3. Now, let's sub into our formula for Tn. From here, we can multiply out the brackets on the right-hand side. N times 3 is 3n, and minus 1 times 3 is minus 3. To clean things up a bit, we can do some simplification. 5 minus 3 is 2. The question asked us to give Tn in the form Pn plus Q. This is precisely what we've done. And we have a 3 in the place of the P and a 2 in the place of the Q. So our final answer here is P is equal to 3 and Q is equal to 2. The next part of the question asks us to find how many tiles are in the 20th pattern. Well, in the previous part of the question, we found that Tn is equal to 3n plus 2. And here, Tn represents the number of tiles in the nth pattern. If we want the number of tiles in the 20th pattern, we should sub in n equals 20 into our formula for Tn. We've found that T20 is equal to 62. So our final answer is that there are 62 tiles in the 20th pattern. In the next part of the question, we have to find which pattern has exactly 290 tiles. Remember, Tn represents the number of tiles in the nth pattern. We want the number of tiles to be 290. So our goal is to find the value of n which makes Tn equal to 290. In equation form, we simply set Tn equal to 290. We found previously that Tn is equal to 3n plus 2, so we can replace Tn with this expression. From here, it's a matter of solving for n. In other words, we need to isolate n all by itself on one side of the equation. If we want to isolate our n, we'll need to remove the 3 in front of it and the plus 2 being added on. Let's start by removing the plus 2. The inverse of addition is subtraction, So to remove a plus 2, I should subtract 2 from both sides. Now, I'll need to remove the 3 in front of the n. This 3 is representing multiplication. The inverse of multiplication is division, so to remove multiplication by 3, I should divide both sides of the equation by 3. So we end up with n is equal to 96. So our final answer here is that the 96th pattern has 290 tiles. Show that Sn is equal to 3n squared plus 7n all divided by 2 is a formula for the total number of tiles needed to build the first n patterns. A useful observation here is the following. The total number of tiles needed to build the first n patterns is equal to the sum of the first n terms of the sequence. And there's a formula on page 22 of the formula book which allows us to calculate such sums. This says that Sn, the sum of the first n terms of an arithmetic sequence with first term a and common difference d, is given by Sn is equal to n over 2 times 2a plus n minus 1 times d. As a reminder, here is a table that we found earlier which contains the first few terms of our sequence. In our formula, a refers to the first term in our sequence, and just like earlier, a is equal to 5. D refers to the common difference, and again, just like earlier, d is equal to 3. Let's sub these two values into our formula. From here, we can do some simplification. 2 times 5 is 10. And for the n minus 1 times 3, we can multiply out the brackets. N times 3 is 3n. And minus 1 times 3 is minus 3. Now, we can combine the number terms inside the square brackets. 10 minus 3 is 7. Here, we have a fraction being multiplied by a term. In a fraction, above the line represents multiplication and below the line represents division. Since we're multiplying by 3n plus 7, we can write this all as one fraction where the 3n plus 7 comes in above the line. Our final step here is to multiply out the brackets. N times 3n is 3n squared, and n times 7 is 7n. So we have shown that Sn is equal to 3n squared plus 7n all over 2. And this is precisely what the question wanted us to do. In the next part of the question, we must find the total number of tiles needed to build the first 30 patterns. In the previous part of the question, we found that Sn is equal to 3n squared plus 7n all over 2. And here, Sn represents the total number of tiles needed to build the first n patterns. We want to find the total number of tiles needed to build the first 30 patterns, so we need to sub in n equals 30 into our formula for Sn. We found that Sn is equal to 1455. So our final answer is that 1455 total tiles are needed to build the first 30 patterns.